So before we get started, I struggled a little bit with this material, and while I think I managed to get the general idea, I might have made some mistakes while trying to clarify certain points. And if that's the case, I'd really appreciate it if you could point out those misconceptions. Nonetheless, I hope that I can help someone trying to cover this material struggle a little bit less than I did. Alright, let's get into this. We will need this preliminary, more technical result before getting to the statement that we are really after. So, given a CW spectrum X, suppose we have another proper closed subspectrum B. So, already B being closed ensures that X mod B is itself a CW spectrum. So assume B is also such that E star of X mod B is 0. So this is the notation for the generalized homology theory associated to E. So specifically, E star X mod B is the graded hom from the sphere spectrum to E smash X mod B. Okay, then there is an infinite cardinal kappa and a closed subspectrum W of X such that W has at most kappa cells. W is not included in B, though they may overlap, and such that E star of W mod W intersect B is 0. So a couple of remarks before we prove this. Firstly, the motivation for this approach to the problem. Now, I'm not entirely aware of the details at this time, but in the paper I was reading, it was pointed out that this cardinality argument put forth by Bofield and I believe one other is necessary because of some set theoretic issues with Adam's initial proof of the statement we are building towards. Part of our larger goal to prove that E-localizations always exist. Secondly, note that if X isn't trivial, um, we can take B to be trivial given that X is E acyclic. This is because E star of X mod B is E star of X, which is a graded hom from the sphere spectrum to E smash X, but E smash X is 0 since X is E acyclic, so the hom is 0. Thus the requirements are met. Okay, now on to the proof. We will want to construct this W inductively. For W1, let it be any closed subspectrum of X not contained in B with at most kappa cells. Such a subspectrum exists because B is assumed to be a proper subspectrum. So now assume inductively that Wn has been constructed. Intuitively, we want to kill every class alpha in E star Wn mod Wn intersect B. To that end, for each class alpha, we can choose a finite closed subspectrum F alpha of X such that alpha goes to 0 in E star of Wn union F alpha mod Wn union F alpha intersect B. Such an F alpha exists because of a technical CW result, that the continuous image of a compact set intersects finitely many cells. So since by assumption E star X mod B, which is the graded hom from the sphere spectrum to X mod B, is 0. So the image of alpha can be extended to a map alpha prime in E star of X mod B equals 0 by the compactness of the sphere spectrum just by adding in finitely many cells. So we can do this for all alpha. Finally, let Wn plus 1 be the union of all the Wn and F alpha. So our indexing indicates each Wn has at most kappa cells. Okay, and finally just let W be the colimit over all of these Wn, and we get our desired result. Now we come to the main result of the video. It essentially says that the property of being E-local is equivalently the property of being quote-unquote A-null for a particular spectrum A. I think this is a pretty interesting result. If you recall our definition of E-local, it wasn't extremely easy to show that something was E-local, but this condition here is easy to verify. Given A, we can just check if the graded hom from A to Y is 0. Okay, let's get into the proof, which is admittedly slightly more involved. So I want to start by constructing A, and then we will prove the properties of A stated in the lemma. So choose kappa as in the previous lemma. Now let the set of K alpha be CW spectra representatives of weak equivalence classes of E acyclic spectra with at most kappa cells. So remember by CW approximation we can always find such a representative. Now we claim that A is equal to the wedge of all these k alpha, and has the properties as described in the lemma. So notice that one direction is straightforward. And by the way, by construction A is E acyclic. But so suppose that one direction y is E local, then the graded Hom from A to y is isomorphic to the graded Hom from 0 to y, which is just 0, because A to 0 is an E equivalent since y is because A is E acyclic, and the isomorphism from AY to 0y is just the definition of y being E local. So that direction is pretty straightforward. Conversely, suppose the graded Hom of A and y is 0. Let C of A be generated by A in the sense that let C of A be the class of spectra that can be obtained from A by taking weak equivalences, shifts, wedges, sumends, and cofibers. Well, then following by our assumptions, we have that the graded Hom of A prime is y. The graded Hom of A prime and y is 0 for any A prime in C of A. We claim that every E acyclic spectrum is in C of A. No, we aren't claiming that C of A is precisely the class of E acyclic spectra, just that it contains the E acyclic spectra. So if we can show the claim, we will effectively show that the graded Hom of an E acyclic spectrum in y is 0, or that every morphism from it to y is 0, which shows that y is E local. Okay, so we just need to prove the claim. So let X be an E acyclic spectrum. Well, by CW approximation, we can assume without loss of generality that it is a CW spectrum. Then, using lemma 1, we can construct a sequence of B lambda, starting from 0, where B lambda plus 1 is obtained from B lambda by attaching W as in the previous lemma. So for each step, apply lemma 1 to X with its closed proper subspectrum being B lambda. The corresponding W we will write as W lambda. So what do we want to show? We want to show that each B lambda is in C of A, and that each B lambda is E acyclic. We will use this to then argue the same for X. So as a base case, certainly B0 is E acyclic and in C of A. Now assume inductively that B lambda is. Well, then take the cofiber of the map from B lambda to B lambda plus 1. The cofiber is just B lambda plus 1 mod B lambda, which is B lambda union W lambda mod B lambda by definition, which is just W lambda mod B lambda intersect W lambda. Well, by construction, start of this cofiber is then 0 using the previous lemma. So the cofiber of the E star of this cofiber is then 0 by using the previous lemma, so the cofiber is E acyclic. Well, since this is an E acyclic spectrum with at most kappa cells, there exists a K alpha from our original definition, A, such that K alpha is weakly equivalent to the cofiber. Remember, we defined the K alpha to be CW representatives of weak equivalence classes of E acyclic spectra with at most kappa cells. Okay, so that makes B lambda to B lambda plus 1 to K alpha a cofiber sequence. Well, then by the triangulated nature of the stable homotopy category, then loop K alpha to B lambda plus 1 is a cofiber sequence. Namely, this exhibits B lambda plus 1 as a cofiber of a morphism between things in C of A. And since C of A is closed under that, this shows that B lambda plus 1 is in C of A. We still need to show that B lambda plus 1 is E acyclic, so E star of B lambda plus 1. Well, by definition, that's E star of B lambda union W lambda. That's the graded Hom from the sphere spectrum to E wedge B lambda union W lambda. We can distribute over that union, then break it up into graded Homs, each of which is 0, hence B lambda plus 1 is E acyclic. The only remaining case to show that this is all true for B lambda is when lambda is a limit ordinal. So in the case that lambda is a limit ordinal, define B lambda to be the following cofiber. So this 1 minus I map confused me when I was reading it. Um, the I is induced by the inclusion of B sigma into B sigma plus 1, so it's the wedge of these inclusions. And so this notation, I believe, is reflective of the stable homotopy category being an additive category. I think 1 is the identity and negative I is the inverse of the inclusions, so I think 1 minus I is just killing off all non-successor sigma summands. Correct me if I'm wrong, I struggle to find any clarification as to this. But in the case I just described, I think it makes sense. The wedges are E-acyclic and in C of A, so by much of the same process as above, we can conclude that B lambda is E-acyclic and in C of A as well. Then x is as x was equal to the last B lambda, and we are done.